All right, get ready, because today we're diving headfirst into the quantum realm. We're talking about something so mind-bending, it makes the rest of quantum mechanics look tame.
It's a wild ride, that's for sure.
You ready for this? Three-particle entanglement.
Now we're getting to the really interesting stuff. Most research focuses on just two entangled particles, and that's already bizarre enough, right?
It really is.
But when you introduce a third particle, things get exponentially more complex, but that complexity, well, it unlocks a whole new level of intrigue.
Okay, so for anyone who just tuned in, let's rewind for a second. We've all heard the buzz about quantum entanglement, that spooky action at a distance thing.
Right, like two particles are linked no matter how far apart.
Exactly. Imagine two coins flipping, always landing on opposite sides, no matter how far apart they are. It's as if they're secretly communicating. That's the basic
Yeah.
idea, right?
A perfect example, yeah. It gets across that inherent connection that exists between the two. But what we're looking at today goes way beyond a simple connection.
Okay, so we're not just talking about more connections with three particles.
Not at all. The source material we're diving into today, a paper called Three-Body Entanglement and Particle Decays, really throws us into the deep end right from the start.
And it's this paper that argues that the very nature of entanglement changes when you bring in a third particle.
That's the crux of it, yes. It becomes a whole new ballgame. To get our heads around this, we need to understand how this entanglement is shared. Imagine it like, say, friendship energy. You only have so much to give, right?
Limited resource.
Right. The closer you are to one friend, the less you might have left for others. There's even a rule for this in physics. It's called the Kaufman-Kundu-Wooters inequality.
So there's like a cosmic rule book that says a particle can only be SO entangled, a delicate balancing act.
Exactly. And get this, the paper uses this very concept, this limited resource idea, to actually measure the different, let's call them friendship levels, between the particles.
I like that. So how do they measure these friendship levels?
They use a measure called concurrence, which essentially quantifies how much entanglement exists between any two of the particles. Think of it like, say, measuring the strength of each thread in a three-way friendship bracelet.
Okay, different types of entanglement, like different braiding patterns. I like that visual. But can we see this in action? How does this entanglement choreography actually play out in real-world particle decay?
Absolutely. Let's look at one scenario the paper details. Scalar and pseudoscalar interaction.
Okay, before we get lost in the jargon, break that down for me. What are we actually talking about here?
Picture a particle. Let's call it particle 0. Now, this particle decays into 3 new particles. And this decay, it happens because of specific forces at play. In this case, a scalar and pseudoscalar interaction. This interaction dictates the specific entanglement pattern that emerges.
Got it. So different forces, different entanglement patterns. Each force has its own signature dance move. So with this scalar and pseudoscalar interaction, what kind of moves are we talking about?
This is where it gets really interesting. In this scenario, 2 of the particles, let's say particle 2 and 3, become maximally entangled, almost as if they're 2 parts of a single whole.
Okay, so far so good. Two's company. But what about...
But particle 1, that's where it gets strange.
Because it's completely independent. It wants nothing to do with the other two.
Exactly. Totally unentangled, just hanging out on its own.
Hold on. So even though all 3 particles came from the same source, one of them decides to just sit this one out. What's going on there?
That's the key. This unique pattern where 2 particles are maximally entangled and the third is totally independent. It's not random. This is a direct consequence of that specific force interaction we mentioned, the scalar and pseudoscalar interaction.
So the force, it's like it leaves its fingerprint on the entanglement pattern. We can actually learn about the forces at play just by observing how the particles are entangled. That's incredible.
That's the beauty of it. And what's even more fascinating is that this is just one type of interaction. The paper delves into several others, each with its own unique signature.
All right, so we're back and ready to untangle more of this 3-particle entanglement mystery.
The plot thickens.
It does. We've seen how one tile of force interaction can leave its own unique mark on the entanglement pattern.
Like a fingerprint, yeah.
Exactly. But like fingerprints, these entanglement patterns, they're not all the same, are they?
You're right, they're not. And that's what makes this so fascinating. Each pattern, it reveals something unique about the forces at play.
Okay, so what other entanglement dances does this paper break down for us? What other patterns are we talking about here?
Well, let's move on to another scenario they explore. Vector and axial vector interactions. Now, remember in the last example, we had that one particle that was completely out of the entanglement loop, just sitting on the sidelines.
Yeah, the independent one.
Right, well, with vector and axial vector interactions, things get a bit more intertwined. Everyone wants in on the action this time.
Oh, so it's a full-on entanglement party now. Tell me more.
Precisely. This time we don't have that clear-cut situation where two particles are maximally entangled and the third is totally independent. Instead, depending on the specific ins and outs of the interaction, we see entanglement possibilities between any of the particle pairs.
So it's like a quantum square dance, everyone's switching partners.
That's a great way to put it. And this is where that concurrence measure we talked about earlier becomes so crucial. Remember, it's like measuring the strength of each thread in our friendship bracelet analogy.
Right, right.
By calculating concurrence for each pair, we can determine how much entanglement exists not just between two individual particles, but even between one particle and the combined system of the other two.
Okay, so a bit more of a complex braid on this friendship bracelet, threads going every which way. But how does this entanglement square dance actually help us understand the universe any better?
Now that is the exciting part. You see, the standard model of particle physics, which, by the way, describes all the known particles and forces, it predicts certain types of interactions. By carefully measuring and analyzing these entanglement patterns, particularly those that arise from these less straightforward interactions like vector and axial vector, we can search for deviations from these predictions.
Deviations. So we're talking about potential clues that there's something more out there, something beyond our current understanding of physics.
Precisely. Imagine we're examining the foundation of a building, searching for subtle cracks.
Okay, I'm with you.
These deviations, even if they seem small, they could point to the existence of new particles, new forces, or even an entirely new framework for understanding the universe as we know it.
This is like quantum detective work, searching for clues hidden in these entanglement patterns to uncover the universe's best-kept secrets. This is incredible. Okay, so we've covered scalar, pseudoscalar, and vector-axial vector interactions. What about that last type of interaction the paper analyzes? They call it tensor and pseudotensor interaction. What kind of entanglement spectacle are we in for with this one?
Now, this is where things get really interesting. We're talking about a whole new level of entanglement complexity.
Yeah.
And potentially a paradigm shift in our understanding of the quantum world.
Okay, you've definitely got my attention. Hit me with it. What's so special about this tensor interaction entanglement?
In this scenario, instead of having clear-cut pairs, or even this constantly shifting dance of entanglement, we encounter something far more profound. All three particles are entangled, yes, but not in a simple, pairwise manner. It's like they're all engaged in a three-way tango, their fates completely and utterly intertwined.
So it's not even like separate threads in our friendship bracelet anymore. It's like they're all knotted together in a way that's impossible to pull apart. We've gone from a line dance to a completely synchronized, inseparable quantum ballet.
A fantastic analogy. And this type of entanglement, where all three particles are inextricably linked, is actually deeply connected to a famous quantum state called the GHZ state, short for Greenberger-Horn-Zeilinger state. This state is considered a cornerstone in the fields of quantum information and computing.
Hold on, are you saying that these particle decays governed by tensor interactions could be a natural source of these GHZ states, the very building blocks needed for quantum computers?
It's a truly remarkable possibility, and we're just scratching the surface here. This research opens up a whole new avenue for not only exploring these complex forms of entanglement, but potentially harnessing their power for technological advancement.
Wow. From spooky action at a distance to quantum three-way tangos and now potentially revolutionizing quantum computing, I need to take a minute to process all of this.
It's a lot, I know.
This is why I love these deep dives. Always pushing the boundaries of knowledge and exploring the most mind-boggling corners of the universe. But before we get ahead of ourselves, let's break down the significance of all of this. We'll be back in a moment to discuss why these findings matter, not just to physicists, but to all of us. All right, so we've gone from simple entangled coins to three-way quantum tangos, and we even touched on the potential impact on something as huge as quantum computing.
We've covered a lot of ground, that's for sure.
It's a lot to take in, but that's what we're here for, right?
Yeah.
To dive deep and explore these mind-blowing concepts. But before we get too far ahead of ourselves, I think it's time for a little recap. For those of us still wrapping our heads around all of this, what's the key takeaway here? Why is this whole exploration of three-particle entanglement really matter?
Imagine, if you will, a new kind of microscope. Not the kind that lets you see tiny objects, but one that allows you to observe the fundamental forces that govern the universe, to witness the very essence of these interactions.
A microscope for the laws of physics, that's a powerful image.
That's essentially what we gain by studying these three-particle entanglements. It's a new lens through which we can probe the deepest intricacies of the quantum world. And who knows what we might find when we start looking through this lens? New particles, new forces. We might even uncover an entirely new framework for understanding the universe.
It's like we're standing at the edge of a whole new world of discovery, and three-particle entanglement is the key that unlocks the door.
Precisely. And something that just occurred to me. Remember how this paper focused on distinguishable particles?
The ones we can tell apart.
Right. But what happens when we take a look at the realm of indistinguishable particles?
Whoa, now you're really throwing me for a loop. We've spent all this time trying to wrap our heads around three particles, and now you're saying there are scenarios where you can't even tell them apart. How does that even work?
It's where things get really wild. See, in the quantum world, particles, they aren't like tiny marbles. They're more like, well, fuzzy waves.
Mm.
And sometimes these waves, they overlap so much that it becomes impossible to say definitively which one is which.
So instead of trying to track individual marbles, it's like we're trying to follow specific drops of water after they fall into a pond. They lose their individual identity and become part of something much larger.
A fantastic analogy. And when this happens, the rules of entanglement, those friendship bracelets we've been talking about, they become even more fascinating, more complex.
Okay, you've definitely piqued my curiosity, but my brain's starting to hurt a little. What makes entanglement different in this quantum soup of indistinguishable particles?
Well, think about it this way. With distinguishable particles, the entanglement is between their individual properties, like their spin, for example.
Mm-hmm.
But with indistinguishable particles, entanglement, it can actually occur between their very existence in specific states.
So instead of two coins being linked, it's more like the very concepts of heads and tails are entangled, regardless of which coin is which. That's next level entanglement.
Exactly. It's a much deeper, more fundamental kind of connection. And the most exciting part is we're only just beginning to scratch the surface of this strange new world.
It's incredible to think that after all these years of studying quantum mechanics, there's still so much more to discover, so many more questions to answer.
Absolutely. It seems like every answer we find just leads to even more questions, and that's what I find so captivating about this field.
It certainly keeps things interesting. Well, that brings us to the end of our deep dive into the fascinating world of three-particle entanglement.
A wild ride, to say the least.
And for our listeners, if you're as fascinated by this as we are, remember, this is just the beginning. There's an entire universe of information out there just waiting to be explored. So until next time, keep asking those questions, stay curious, and we'll see you in the next deep dive.